Alright, hey, welcome back, ninth graders. Today we're going to be talking about simple machines. Over here you can see one simple machine in action. I'm going to show you that one a little bit later. That's the pulley. The pulley system is probably one of my favorite simple machines. In this diagram we got just kind of a little cartoon here. There's a bunch of different simple machines in action. You got the lever right here. You got the elephant walking down a ramp. You maybe got a little pulley system here in the cord. So just kind of a funny little cartoon. It's called the labor saving auto jack. What you do is when the rear flat tire goes flat, you're going to pull on string A, fire peanut. Over here, the elephant sees the peanut, walks down the platform, steps on here, lifts it up, hence the name auto jack. Funny thing about the cartoon is if you get a puncture in the front tire, call a cab. So just kind of a funny little cartoon there. So we're going to be learning about 6 types of simple machines today. There's going to be the lever, which you saw in the cartoon. This is the lever. We're going to be learning about the wheel and the axle system, the inclined plane, the wedge, the screw, and my favorite, the pulley, which is over there. So let's get this thing started. So a lever, like what is a lever? Well, a lever is a rigid bar that is free to move around a fixed point. The fixed point of the bar rotates around is called the fulcrum. So I can give you an example of a lever. In that previous problem, we looked at the crowbar, and the crowbar was lifting up on the box. So a crowbar is considered to be a lever, okay? And right here, the point at which it pivots is called the fulcrum. So right here, this is called the fulcrum. So that's basically what a lever is. It's a rigid bar that is free to move around a fixed point. Free to move around the fixed point, which would be right there. That's the fulcrum. All right, the input arm of a lever is the distance between the input force and the fulcrum. So if you think, well, I can label this for you again. Let's go like this. So if we have our crowbar, this would be the input arm. Okay, that's going to be the distance between the input force and the fulcrum. The output arm, which would be down here of our lever, is going to be the distance between the output force and the fulcrum. Levers are classified into 3 categories based on the locations of that input force, the output force, and the fulcrum. There's actually 3 types of levers that I'm going to teach you about. We have first class levers, second class levers, and third class levers. I'll give you examples of all of these. So a first class lever is like the crowbar. It gives us a mechanical advantage greater than 1. So the fulcrum is going to be located in the middle. So with first class levers, the fulcrum is located right here in the middle. If you take a screwdriver and try to open up a paint can lid, that would be a first class lever. The fulcrum's right here. This would be the input. The output force is way over here. That gives you a lot of force. Now, the closer the fulcrum goes to the output force, the more of a mechanical advantage you're going to get. The closer it is here, the less of a mechanical advantage you're going to get. And like it says right here, the mechanical advantage can be greater than 1, equal to 1, or even less than 1. Especially if the fulcrum was way over here and you had to try to pry on it, you're not going to get much of a mechanical advantage. So that is a first class lever. Let's talk about second class levers. Second class levers would be like a wheelbarrow. So if you look at a wheelbarrow, the fulcrum, the pivot point, is on the tire here. So then you might be wondering, well, what's the output force Well, the output force is what you're actually putting inside the wheelbarrow. The input force is over here. So if you look at what's different, it's where the fulcrum is positioned. So with a first class lever, it's in the middle. With a second class lever, the fulcrum is going to be over here, and right next to it is going to be the output force. So that's why I like to say the wheelbarrow as an example for second class levers. So you're going to have the fulcrum, then output force. The mechanical advantage of second class levers is always going to be greater than 1. So it doesn't matter. So if this force is here or even close to the fulcrum, anywhere you move the flower pot along this, you're always going to get a mechanical advantage greater than 1. Now, if you've ever had any experience with wheelbarrows, you know that if you put all the weight right here, it's harder to move around. If you move it closer to the fulcrum, the easier it gets. So next time you guys use a wheelbarrow, practice that. You'll see, if you put the majority of whatever you're trying to haul in the front, it's actually easier to pick it up. It's easier to move it. So, all right. So that's a second class lever. Let's talk about a third class lever. Now third class levers are they're like the opposite in terms of mechanical advantage. We don't get a mechanical advantage out of a third class lever. It's actually less than 1. But if you're looking at a broom, for an example, if you take it and if you're picturing right here and you're going like this, where is it pivoting? Well, it's pivoting down where? Where is it pivoting? Right here, isn't it? So it's pivoting on the hand. So the fulcrum is right here. What's the output force? So it's down here. What's the input force? It's your hand actually moving it. So you might be wondering, well, what's the difference between a third class lever and a second class lever? Looks like the fulcrum's on the outside. Well, if you look closely, it's where the output force is going to be located. So the output force is in the middle with a second class lever, and the input force is going to be in the middle with a third class lever. And if you've ever used a broom, you know it takes a lot of effort to really broom, because the fulcrum's right there and the input force. So it's actually more work. So that was the 3 levers. Let's talk about the wheel and axle. The wheel and axle is a simple machine that consists of 2 discs or cylinders, each one with a different radius. The outer disc is the wheel, and the inner cylinder is the axle. They rotate together as one unit. You can think of a screwdriver as being a wheel and an axle system. The wheel being the handle, the axle being the actual thing doing the turning on it. So when the force is applied to the wheel, you're going to get a mechanical advantage. But when the force is applied to the axle, you don't get a mechanical advantage. So here's some pictures of a wheel and axle system. So here's a screwdriver. So if you use this handle to turn over here, if this is the input and this is the output, you get a greater mechanical advantage. If you actually try to use this to undo the screw, you don't get much of a mechanical advantage. The outer disc needs to be bigger than the inner disc.
Jessica Deeds, can you please call
So
me at
that was the wheel and axle. Let's talk about inclined planes.
Please call me at 8818.
Inclined planes is a slanted surface along which a force moves an object to a different elevation. So that's like the ramp example. So we use ramps to help us lift objects up. I have a ramp system to get my 3-wheeler in the back of a truck. It's a lot easier to push it up a ramp than it is to pick up the whole 3-wheeler and put it in the back. Even though it can be done, 2 guys can pick up the 3-wheeler and put it in the back, but it's a lot easier to use the ramp. So ramps give us a mechanical advantage greater than 1. This is kind of why, if you've ever taken a trip through the mountains, this is why on hillsides that they curve back and forth and back and forth. because it actually gives us a nice ramp system to go up and down versus going straight up. Well, actually, you guys should know that because the mountain bikers around here, we don't just go straight up and down the big hills here in the Cuyuna Range. We have things that go up and down and wind back and forth. So it's a simple machine. It makes it easier to go up and down the hills. So it's a ramp. All right, so now let's switch gears. Let's talk about wedges. So a wedge is a V-shaped object whose two sides are essentially inclined planes. A wedge always gives us a mechanical advantage greater than 1. This would be like an example of a wedge. They are typically used to help split firewood when you get a stubborn, big piece of firewood. So that's a wedge. Let's talk about screws. Basically, a screw is an inclined plane wrapped around a cylinder. That's really all it is. So if you kind of look at right here, it's basically an inclined plane that gets wrapped around a cylinder. So I'll go back. A screw always gives us a greater mechanical advantage. It makes things easier. The closer the threads of a screw, the easier it is to turn it in. The more farther spread out those wedges are, the harder it's going to be. So what I mean by that is the thread of these screws. So like this one's a little bit closer. That one's going to be a lot easier to hand turn in. When these inclined planes get spread out, it's going to be a little bit more difficult to get them in. So yeah, that's going to be screws. The last thing we're going to talk about is pulleys, which is kind of like my favorite one. I got one set up here. I'll show you what they do. A pulley is basically a simple machine that consists of a rope and a wheel. Pulleys produce an output for, well, pulleys give us a mechanical advantage for the most part, but it can also give us an equal mechanical advantage, which I'll take that all apart and I'll show you what I mean by that. But typically, a pulley gives us mechanical advantage, or it's just going to be equal to 1. So for example, if we have a fixed pulley, so I'll take this thing apart and I'll just show you the one pulley. A fixed pulley gives us a mechanical advantage equal to 1. It helps us lift it up, but it's not giving us a mechanical advantage. It's just equal to 1. So for example, if you got an object that weighs 4 newtons and it's wrapped around one fixed pulley, meaning this isn't going to move, it's going to take 4 newtons of force to lift it up. So 4 divided by 4 is 1. But here's the deal. So this is the one case where the pulley doesn't give us a mechanical advantage when it's fixed. But if you take that same pulley and you attach this to the ceiling and you have it down here attached to the block, now this thing is able to move up and down. It gives you a mechanical advantage equal to 2. Which is a little bit of a mechanical advantage. The more pulleys you add to it, the easier it's going to be to lift the object. And there's actually kind of a fun way to figure it out, to do the math. If we have a 4 Newton object right here, if you count the number of strings that are going to be used to support the weight of it, you actually just take and divide it by the number of strings that is supporting it. So for instance, we have 1, 2, 3, 4 right here. The object weighs 4 newtons. It's only going to take 1 newton of force. So actually that's what I have set up right here. I'll maybe get the camera turned so you guys can see that a little bit better. Let me go like this, get it turned towards the pulley system. Maybe even I'll just show you this. So this is actually a 3 and 3. It's a triple pulley system. So it's got 1, 2, 3, and then down here 1, 2, 3. If you're looking at the system, this is actually a good view of it. If I kind of go like this, you can count the strings supporting the load. It's 1, 2, 3, and then this side 4, 5, 6. So if you're doing the math at home, whatever it takes to, whatever this thing weighs, it's gonna divide it by 6. So for fun here, let's do that. So I'm gonna set this here like this. Actually, you know what? I'll maybe just go like this, and I'll show you on the scale. So down here, I actually have a Newton's scale right here. There you can really see the 6 strings. If you look, get this in focus, right there. Well, it's saying about 2 on my scale here. And now the object actually is 1 kilogram, or it'd be about 10 newtons. It'd actually go all the way to the top. So this thing makes this, it's actually really easy to sit here and move this thing up and down with those total of 6 strings. So, all right, I'm gonna actually put this back. We'll get this thing set back up. So yes, pulleys are great. I have a pulley system that I use in my garage. Wait for this thing to focus, come on. Maybe it needs to see a moving object here. I don't know, maybe I should have just left the phone as is. Why don't you focus? Come on. Focus right there. Focus. There we go. Okay, so yeah, I have a pulley system in my garage, which I use to take my portable fish house up and store it in the ceiling. And I can do that as a 1-person operation with the help of a pulley system. If I were to try to hang that same portable by myself without a pulley system, there'd be no way I could do it. It just weighs too much. Let's talk about compound machines real quick. So a compound machine is a combination of 2 or more simple machines that operate together. So a watch is a compound machine. I like to think of a bow and arrow as being a compound machine. So yeah, a bicycle is a compound machine. I think what I'll do is I'll let you guys answer these questions on your own. They'll be in a Schoology assignment 14-4.